just do the quick introduction here. So welcome to the next PCC webinar. And I'll just give you a quick introduction, very quick introduction to IAPS and the PCC working group before I hand over to Barry Dooley and Wolfgang Hater from the Power Cycle Chemistry group, who will be delivering this webinar on film-forming substances. Barry and Wolfgang world leaders in this area, leads on developing the original IAPS technical guidance document on this, and both very, very active in this area. Questions, please put your questions into the chat and we will address the questions at the end of the webinar. And we'll go through those. And the webinar is being recorded and will be posted on the IAPS PCC YouTube page that you can find just by searching IAPS on there, and there'll be a link on the IAPS website to it. So just quickly, objectives of IAPS, some associations to advance knowledge and properties of water and steam and aqueous systems, particularly around industrial importance, and make that knowledge freely available to engineers and scientists the world over. So these webinars are part of that outreach to share information and help people in industry out around the world. So it's been around since 1929. It's an association of national organizations managed by an executive committee, and there's an annual meeting. Everyone's invited. Anyone can come along, but and then there's a more major conference every 4 to 5 years. So current members, you can see here, and you can find this on the IAPS website. Full members, and then there's associate members. So we would like to see some more countries get national committees together and become active in IAPS. And then IAPS, we have an executive committee, and then there's kind of 4 working group parts in the physical properties of water and steam. So this is where steam tables have come out of. Industrial requirement solutions, this is more related to steam turbines, industrial manufacturers. Physical chemistry, aqueous solution, this is sort of the main sort of research part of IAPS. And then power cycle chemistry, right, where the application practical side, and this is where this webinar has come from. And if you work in a power plant, you've used IAPS because that's where the steam tables came from. Okay, so every power plant in the world, any plant that uses steam is anchored in IAPS publications and information. Power Cycle Chemistry Group, if you go to the IAPS website, you can find a description on PCC. The current chairs and our contact details are here, and you can find them on the website if you have any other questions. So myself, Paul McCann, Kirk and Taro there. So we welcome any correspondence and any interest in PCC. And then you can find our technical guidance documents on the IAPS website. These are all free to download as PDFs. And there's a wide range there covering almost all aspects of power cycle chemistry for plants, and there's more in development and more coming. And you can get the webinars, and there's a white paper which is on corrosion product sampling, which is very, very interesting as well. And you can access the webinars there. And just a note, our next webinar is intended to be on STEM chemistry phase transition zones, and this is planned for March. We'll get notifications out for that shortly. Other international meetings coming up. The IAPS annual meeting is June, July. That's in Bristol. This is the main working kind of meeting, sort of hybrid conference working meeting. Everyone's welcome. If you have any questions, reach out to me and we can help you out there. There's a couple of other related events that IAPS has some involvement in. The European HRSG forums coming up in May in Italy. You can see the website there. There's an HRSG forum in the US. And as I understand it, there will likely be another HRSG forum in Latin America. Details will be coming out for that. There's also a boiler and HRSG meeting in Australia, and that'll be probably November 2026, dates to be confirmed. And then if you go on the IAPS website or you look at the LinkedIn page, you'll see local IAPS groups meetings as well. So there's just an example, the ones that I know of right now. Dutch IAPS meetings in March, the German Swiss is in March as well, and New Zealand's going to be in September. And you can find that information online, and you're all welcome. And then also a massive shout out to the Combined Cycle Journal for hosting the webinar for us. So Scott and the team there. You can go to CCJ-online and find all their info. So big shout out to them for helping us out. And then now I'm done. I'm just going to hand over to Barry and Wolfgang to go through. Again, put your questions in the chat and we'll work through those at the end. So over to you, Barry and Wolfgang. Thank you very much.
Wolfgang is going to give the first half.
Start, yeah. So I will share my screen now. So now I have to go to presentation mode. Zip. I have to put this away. And the pointer. So now I'm ready for takeoff. So first of all, also welcome from my side to our webinar on the application of film-forming substances in power cycles. So Barry and me, when we prepared this webinar, we agreed upon the position that the film-forming amide technology, or more generally spoken, the film-forming substance technology, is the most important addition to cycle chemistry since many years. But we all also agree that there is lack of scientific background and understanding. So in this case, the practical application is already since a couple of years ahead of the science. So is this a new technology? No. The first papers that were published, or patents, are already dating back to the 1940s. And since then, there has been developed a lot of know-how that is officially available. There are several applications in water treatment. So we are talking about cooling systems, geothermal, and what is the subject of today, power cycle chemistry. There's one point which is a little bit difficult. There's hardly any publication or scientific paper on the non-disclosed film-forming substances. So if you want to have a comprehensive view and a summary of the knowledge about film-forming substances, the application of film-forming substance in the power cycle chemistry, I only can recommend you to go to the IAPWS homepage and download the 2 international documents, technical guidance documents on the application of film-forming substances, either in fossil combined cycle and biomass power plants or in industrial plants. They give you a very excellent overview about the technology. They give a comprehensive literature, a list, and guide you all through the questions that you have to ask. I would like also to mention that IAPWS is developing a certified research need that will be published soon. The intention is to make a list of scientific gaps that should be closed for both FFA and FFS. So in the last years, there has been a tremendous amount of activities dealing with film-forming substances. There have been numerous plant assessments, various case studies reported, and application instances worldwide. And that's also an important issue, that there were 7 international conferences dealing only on film-forming substances. And this shows the interest, the general interest in this technology. But let us first look, what is a film-forming substance? This is a corrosion inhibitor. A corrosion inhibitor for a power plant that is operating and a power plant that is in standby. And it works, simplified way, by absorption onto a metal or metal oxide surfaces. If you look on the application, we can categorize 2 different principles. One is that the film-forming substance is added additionally to a base cycle program, basic cycle chemistry program like AVTO, PT, or OT. In this case, of course, you should first optimize the basic chemistry program before adding a new component. But there are also applications where the film-forming substance is in an all-in-one product that provides a full treatment. In this case, it is blended with other components, for example, to achieve the pH control, etc. What is common to all substances is all film-forming substances. They are organic molecules. They have two parts, one hydrophilic that contains a nitrogen and or an oxygen atom, or maybe some else, or a hydrophobic part that is generally a long carbon chain. So it acts also like a surfactant. Generally, the solubility of these substances, these molecules, is not too high, but in the conditions, in the application concentrations that you generally have in the water-steam cycle, they are soluble. A very important property is their steam volatility, which certainly the amount of steam volatility depends on the molecule itself, which enables the film-forming substance to protect the inner surfaces of the full water-steam cycle. There are some doubts whether under dry steam conditions, like you find them in the superheater or reheater, these molecules are able to form a film. But there is a very new study that will be published soon that shows that at least one film-forming amine is able to adsorb under these conditions. So the conclusion is it can protect the full water-steam cycle, also the dry steam parts. So when we originally started working on the TGDs, we had a big mess up of names. This name, then there were film-forming amine, polyamine, fatty amine, surface active agent, and so on. And so the IAPS decided to introduce a nomenclature which is now getting more and more internationally accepted because it creates clarity. So we now know what we are talking about. And there was an important distinguishing between the molecule itself and the commercial product that you apply in your plant. And of course, the commercial product, one part of the commercial product is the film-forming substance. And this is differentiated between film-forming amines. These are three very well-known molecules that are disclosed and where the properties are publicly available. And non-disclosed molecules, which we call film-forming products. If we look on the experience that was gained in the last decades on the application in the power cycle, we find that there are significant benefits that were provided by an application of a film-forming substance. I have selected 5 key points that are repeatedly reported, which I will show you later in a little more detail. What I would like to point out that almost all of these effects will improve the economics in the water steam cycle. For example, it has been shown that after an application of an FFS into the water steam cycle, it was easier and faster to achieve the steam quality that is necessary to start the turbine running. And of course, if you can start the turbine running more early, you can make more money. But I would like to go into more detail in the next slides. So Reduction of iron and copper levels. Here you can see an example of iron data from a combined cycle gas turbine plant. This plant is operating in heavy cycling mode and was exceeding the recommendations of the IAPWS guidance by far. So this plant was operating in a traditional way with AVTO plus phosphate into the drums, except the high pressure drum. At a certain time, they decided to add a film-forming amine to the water chemistry, and what you can see in the bars is the average iron level that dropped markedly after the introduction of a film-forming amine. These are average values taken by grab samples over a period of 9 months, so they have very high statistical significance. And such kind of effect has been reported repeatedly. Improved shutdown protection. You can use film-forming amines to protect the plant during a dry standby or a wet standby. On the right-hand side, you can see a picture of a feedwater tank during shutdown protection. You can see no traces of corrosion anywhere. This system has been treated shortly before it was shut down with FFA, then emptied and dried by the residual heat of the plant. But not only if the plant is in dry standby, also if it is in wet standby, you can have a good protection. This chart shows you the development of iron in a simulated layup solution treated with different agents. DI water, AVTO, and FFA. And you can clearly see that the total iron in the layup water that contained FFA is practically zero over almost 1 year. That's an indication that you have an improved standby protection compared to the AVTO treatment alone. Efficiency improvement. Efficiency improvement turns out to be a very high economic advantage. 2 examples are shown here. There are more published in the literature that I don't have the time to spend on. On the left-hand side, this graph shows data from several paper mills where an FFS was added to the steam dryer to dry the wet paper. And the specific steam consumption before and after the start of the FFS dosage is shown in this graph. The red bars show it before and the other bar below, after the FFS. And you can clearly see that the specific steam consumption, what you need to dry the paper, is reduced. And this is about, in the average, 3%, which is a significant saving for the plant. Oh, excuse me. On the right-hand side, you can see the results of a study done in the Moscow Power Institute, where they found out that an increase that with octadethylamine in the inlet turbine steam, the turbine efficiency could be improved by up to 2%, which is again a drastic economic advantage. I think this is something that is in front of the demand to reduce CO2 emissions, a very important effect that should be followed more closely. Plant cleanliness. When I'm participating to inspection of operators that first time open their plant after they have switched to an FFS treatment, I often get the remark, "Oh, very clean," or "exceptionally clean." Beforehand, I had to take out 1 bucket of debris on the drum. Now it is hardly one handful. This is, of course, a qualitative effect, but in the upper 2 graphs, you can see also we can see a quantitative effect. This graph shows two cross-sections from tubes of an HP evaporator. Until 2013, this evaporator was treated without FFA, and from 2013 up to when this sample was taken, 2 years, it was treated with FFA. You can see a marked difference because this loose iron oxide has vanished. So we can see a very significant cleaning effect that will improve the heat transfer, but also maybe even omit a chemical cleaning. About chemical cleaning, Barry will talk about more in detail in the second part. Now, have a closer look to the chemistry. I start with the film-forming amines because there we exactly know what it is. So we have an amine functionality and a long carbon chain. There may be two amine groups or saturated or non-saturated carbon chain. What is common, the common opinion is that the molecule attaches to the surface via the nitrogen atom, involving the p electrons of the free electron pair. For the film-forming substances, we looked into the literature, into the patterns, where there were suggestions what you may use in the field. So again, and we have taken some of these structures here on the page. You can see there is a hydrophilic part and a hydrophobic part. So the principle is similar, but the chemistry is of course different. There is a common mode of action, and that is the adsorption to the surface. The common knowledge is that the adsorption takes place via the hydrophilic part, in case of the filming amines, via the amine section, in phase of the FFS, via the hydrophilic part. And the hydrophobic part turns out into the water phase to create a hydrophobic surface. And this hydrophobic film has been thought to protect the steel by decreasing the contact between water and metal. If you don't have any water, the corrosion will be reduced a lot. This is, of course, a simplified model. Today, our knowledge about the mechanisms is far ahead, advanced, but it's still to illustrate the effect. What also illustrates is that if you take a water sample and want to analyze the film-forming substance in the water, you don't get what is on the surface. That must be clear. And this is also why you never find in the water what you dose, because a part is attached to the surface. Now, what is available on the market? And there is a wide range of commercial products and suppliers. If we look to the products, as already mentioned, there are two major categories. One, and these are the products that are added supplemental to the base chemistry program. They consist mainly on a filming component and can also have an emulsifier to create a storage stable blend. And there's the other one, that is where you get a full cycle chemistry program. Besides the filming component, in these cases, you have further additives like alkalizing agent. This can be alkalizing amines, sodium hydroxide phosphates. They might contain dispersing agents or even reducing agents. Now you can see why it is important that the operator knows the composition of the applied product. You must understand what the product is doing, what it can do and what it cannot do. Also, if you don't know the chemistry, you cannot judge if there are any risks related to the application. But for researchers, the variety of commercial products makes the life a little bit difficult. The intention normally is to create some generic understanding. But if you tests a commercial product, you cannot transfer the results from one commercial product to another commercial product, especially if it is not the same firmware inside. So for the analytics, of course, as for all treatment programs, a careful analytics is essential. For the film-forming amines, there are two basic systems, two basic methods. One is a cationic surfactant, and the other one is the reaction with a selective dye. There are different dyes on the market, but Bengay Rose is the most important one. These analytics can be done via grab samples. There are test kits on the market, and there is can be done photometrical determination with a standard spectrophotometer, and the reagents are commercially available. Also for the FFA, there is an automated method of analysis available based on the Bengay Rose method that has proven its worth already in the field. Besides the direct measurement, you can indirectly conclude on the presence of the filmer in the water if you implement test specimens into the water cycle, for example, in the sampling lines, and remove the test specimen and are able to detect the filmer on this specimen later. But I will go into that a little bit more detail. For the film-forming products, there are vendor methods, various vendor methods. I would like to add one general comment to the analytics. For sometimes I've seen the recommendation that you should measure the TOC or COD or another parameter that includes multiple groups of chemicals. These are not suitable for control. They give you data, but these data don't tell you anything. So we have covered the analytics in the water. Now we go to analytics on the surfaces. The most important test on the presence of filmer on the surface is the hydrophobicity. You spray a droplet of one or more droplets of water to the surface, and if you have a nice round shape, it's hydrophobic. If it looks like that, it is hydrophilic. In this case, it is assumed that film is present. There it is not. This is very commonly used. It's not standardized. Everybody does it a little bit different way. But keep in mind, this is not specific for filmer. You can create a hydrophobic surface also with oil. And what has been understood now, that there are not only false positive, but also false negative. So especially if you have iron oxide on the surface, the interpretation of the droplet test can be very tricky and can lead to misleading results. Another issue is that it tells you that it's hydrophobic, but the level of corrosion protection is not really clear. Besides this qualitatively test, we have now a semi-quantitative test for the determination of film-forming amines on the surface. This can be done on-site. The principle is that you remove with a solvent the film-forming amine from the surface, transfer it into an aqueous solution, and inside of the aqueous solution, it is determined via the normal Bengay Rose method or an adapted Bengay Rose method, which is a good step in advance. Of course, you can use, for very detailed analysis, very sophisticated surface analytics, especially to mention is photoelectron spectroscopy and infrared spectroscopy. These analytics you can do only off-site if you take a sample and send them to a laboratory. Good. As I already mentioned, all filming molecules are organic. As a consequence, they face partial decomposition, especially in the hottest area like the superheater and reheater. For the film-forming amines, this is well studied and understood. And the main decomposition products are ammonia and low molecular weight acids, and more predominantly acetic acid and formic acid. These two acids lead to an increase of the conductivity after cation exchange, or acid conductivity, and thus have an impact on the steam. But it is possible to operate a plant like it is shown here with an FFA dosing and maintaining at the same time the specification of steam purity for the steam that is leading to a turbine. For the FFP molecules, I don't know any scientific study published. I already mentioned the property of filming amines that they have a cleaning effect. I showed you that a porous iron oxide layer has been removed slowly, which is, of course, a positive effect. But there's also have been oppositional effects observed when using these molecules. This is related to the buzzword gunk balls, that are deposits that look a little bit like balls. I took this picture from a paper from 2012. With the risk of deposit formation and the amount of deposits, the risk of under-deposit corrosion increases. And it is not 100% clear when the positive effect turns into a detrimental effect. But what is very clear that with increasing amounts of internal deposits and increasing film dosage, both lead to increased risk of deposit formation. As a consequence, you can understand why the assessment of internal deposits and maybe a cleaning of the plant is important to avoid these problems or these risks, or to minimize these risks. At the same time, a careful dosage and a careful dosage control is mandatory. So, how to dose and how to monitor? Oh, sorry. Preferably, the film-forming substances are dosed automatically into the condensate or into the feed water pump inlet, and the amount should be controlled by the feed water or the condensate flow. Keep in mind that in case of non-volatile components in the product, the dosage must be after the branch of the spray water to avoid any pollution with phosphate or sodium of the turbine. Generally, a single dosing point is enough to cover the whole plant. Keep in mind, the film-forming substances are steam volatile. But in special cases, a second dosing point can be advantageous. For example, if you want to create the film in an air-cooled condenser, which has a tremendous amount of surface. Also, it is known that some filming products can attack plastic materials. For example, the film-forming amines attack Viton. This is known, and as a consequence, you should check with the vendor the material compatibility and, if necessary, exchange the materials. I would like to emphasize that this is valid only for the parts that come into contact with the concentrates. In the application concentration, this is not relevant. I can only repeat, avoid overdosage. It has been a very good practice to start a dosage with an initial lower amount to what is finally aimed for. And after everything has come to a smooth operation, increase the dosage. Another point is that many of these products are emulsions. And emulsions normally should not be diluted. If they are diluted, you should take care that there's no phase separation, because if there is a phase separation, you add water or a high amount. The monitoring. Of course, you should measure the FFS residual in water, but additionally to the normal parameters according to the TGDs of the IAPS, like pH, conductivity, and so on. So, if you now want to start an FFS application, what should you do? In this case, Chapter 8 of the two mentioned TGDs give you detailed recommendations. I only repeat here the most important parts. You should do an assessment of your plant status and analyze possible risks. For that, you must understand what is inside of the FFS commercial product. Otherwise, you cannot judge it. Furthermore, you should define targets, what you want to improve. Do you want to reduce the metal concentration in the water? Do you want to have a faster startup? Do you want to improve plant protection? And define ways how to measure this, how to determine the degree of this effect. Don't forget to train the people, because film-forming substances behave different from ammonia, for example. Especially the people who do the analytics. They should know how to take a sample. They should know how to do the analytics. Just not black magic, but you can do a lot of mistakes. And don't forget that you should do a baseline determination of the important parameters for the current cycle chemistry. Whatever you have defined for targets, you should measure with them this data for the current cycle chemistry. And after the changeover to an FFS treatment, validates the target achievement. This you can do only if you measure the data again. And then, of course, we assess the plant status. And if you don't do a baseline determination, how can you evaluate whether it's a success? This is not only valid if you want to start an FFS application, but in case of any change of treatment program, you should do that. Good. Now let's imagine you have done for a certain time a treatment with an FFS and you're not happy, or due to some reasons you want to change. Can we change between different FFS products? Let's first look to an FFS dosage that is supplemental to a base chemistry program like AVTO or whatever. In this case, it's easy. You stop the dosage of the current FFS, you clean the dosing system, which is very important. You operate the system a couple of days without FFS dosage, and then you can start the new the dosage of the new FFS. The protective layer will be reassembled over the time. I would not at all recommend to mix the commercial product in the storage vessel. This will normally create a lot of trouble and mess. In case, if you use an FFS product that provides full cycle chemistry, it is not so easy, and you have to have a case-to-case evaluation, how to do it. So, with that part, I would like to stop my presentation, and I would like to hand over to Barry, who will lead you to the second part of our webinar. Thanks a lot for your attention.
Good. Thank you, Wolfgang. Can you unshare, please?
Didn't I unshare?
Okay, I'll have a look.
Oh, what happened?
Go ahead.
I stopped sharing, not?
Okay. All right, I'll see if I can share. Let's see.
Good. Because now I see your face.
Okay, and so this one here. This should be your last slide.
This is my last one, yes?
Okay.
So I will switch off now my audio.
Okay, thank you. And just need to get rid of this audio. Okay. There we go. And so let's proceed here. So Wolfgang's left me a few minutes here to present this to you. So from Wolfgang's part one, you've seen the indication of the format of the IAPWS TGD and some of the known science. And most importantly, because this part will be different, he's shown you some very good applications. I'm sure we'll see in the question period that that all applications are not the same. Some are good and some are bad. And I want to show you in this second half some of the applications which we've seen that have resulted in some failure. And also, I'm going to show you the tools in a little bit more detail than Wolfgang just mentioned very nicely on how to do Section 8. So this first slide that I show here is just let me turn my video off, and that should be okay. So this just shows you a summary of some of the features that Wolfgang mentioned. What we generally see are universal reductions in feed water ion. But what we want to emphasize is that there's no equivalent understanding from anybody about what the mechanism of oxide growth reductions are. And I'll talk about that in some detail. He's mentioned about the general observations of hydrophobic films on water touch surfaces, but it's underlined that hydrophobicity does not prove the presence of a film or any protection. And we generally see good shutdown protection on water touch surfaces, as he's mentioned, but film formation and protection remain very questionable on steam touch surfaces. And that's because the growth of oxide on steam surfaces is not a function of the chemistry. When we come to FAC, it's very difficult to see FAC being reduced, flow accelerated corrosion being reduced, other than by measuring the iron, and most often measurement of iron is not done properly. So what I'm going to show you is one application in an air-cooled condenser where FAC can be seen. And what I'm going to show you just at the beginning here are a few problems occurring in plants worldwide, but have not been openly published. We've tried to publish them in the 7 conferences, but not universally published. So these are things like internal deposits, tube failures, especially under deposit corrosion. And I think there's a new boiler tube failure mechanism here as well. Formation of gunk or gel-like deposits in drums on heat transfer surfaces. So here's a few examples of the many that we've analyzed. Just got to go here. So this was one of the first ones we saw over 10 years ago. We didn't quite know what was happening at the time. So this was tube failures in HP evaporator due to heavy deposits. You can see the details of the unit here. You can see the internal surfaces with very heavy deposits and the failures that took place. And when we make a cross section here, you see that there's a very thick and dense corrosion product layers. And when we cross section it, you can see right here that this is what we call an under deposit corrosion mechanism. And the scale here is in typical multi-laminated morphology. That means that it's very fast. But the interesting thing here, when we see these in FFS units, is that we don't see the material degradation. And so now, after collecting these examples for over 10 years, I think that this is a new HRSG tube failure mechanism that's taking place. So we're in the in the initial process, thoughts of making a few additions and changes to the TGD, and one of those would be to add some clear direction as to when an FFS can and cannot be analyzed. So here's an example that you see. We would not like you to add a film-forming substance to this situation. Here's analysis that we did from internal servers. You'll see that the total loading here is very high. And when we look at the IAPS deposit map, which I'll describe in some detail in a little while, that's right up here at the top of the red area. And so that was in an HRSG. We also want to indicate that the same thing can happen in fossil water walls. We also look at those. We've looked at many of those. This is just an example from the boiler is described here and the loading. You can see after the application of an FFS, there's a large increase in the amount of deposit. And the most important thing that the IAPS decay map, the IAPS deposit map indicates, is that once you get this reaction product, which is this black layer at the base of the deposit, then you want to be very careful about adding an FFS. Or you might end up with a situation that looks like the one previously I showed you, or this one. This was a failure that occurred in a triple pressure HRSG. And you can see here the under-deposit corrosion taking place. And when we look at this in detail, metallographically, we find examples like this. You can see very clearly this very fast occurring rapid process of a multilaminated scale, and the same here. But again, we don't see any material degradation, which is normal in an under-deposit corrosion situation. And so again, I think that this is a new tube failure mechanism. It hasn't been quite worked out yet, but we're seeing too many examples of it now. And that relates to the deposit map again, which I will talk about in a few minutes. The other thing that Wolfgang mentioned was gunk deposits, and I'll show you that in the next slide. And so we want to make sure that if you don't look at these internal deposits, you've got to be very careful of increasing HP evaporated deposits, which can go to high enough levels that can initiate under deposit corrosion. So this was a detailed study that we did, and you'll see after 3 or 4 years, we measured the internal deposits. They were still down here in the yellow area, so not quite as harmful as in the red. But when at this time, this organization decided to apply an FFP. You know what an FFP is now from Wolfgang's discussion. And this then, 1 or 2 years later, had increased this deposit level. The deposits had increased by up to 3 times. So you've got to be very careful of these deposits. These are typical of the gunk deposits that we see on low pressure drums and on steam turbines and other applications. And I already mentioned that FAC was difficult to see, but in an air-cooled condenser, it's relatively easy to see. So this gives you an example of FAC, two-phase FAC in the tube entries right here, with a very high DACI. This is the corrosion index of 4. The highest it can go is 5. All these white areas indicate lots of FAC. And after using an FFP, then all of those white FAC areas disappear, and the DACI went down to the lowest level. So this is equivalent to having hundreds of ppb of iron coming into the condensate compared to less than 10 ppb of iron coming into the condensate. So now I've shown you a couple of the things in a short period of time. I don't have too long to show you, but I've shown you enough to indicate that we have to be a little careful here. And so Wolfgang mentioned Section 8. I want to go into that in a little bit more detail. We covered that in the TGD documents, the FFS documents, but I want to show you the supplementary information that's needed that we didn't go into in too much detail. And so these are involved with measuring total iron in steady load plants, measuring total iron in flexibly operating plants, and measuring the internal HP evaporator internal deposits. And I'm going to just talk a little bit about each one of these, starting with the first one. And that's this IAPS TGD 613 that we developed in 2014. And this was the first document that IAPS produced to be involved with sampling and analysis of corrosion products. It included what were non-suitable methods. They're given here, spectrophotometer in the lab or millipore filters, and that's because the detection limit is not good enough. You've got to have the detection limit to show that you've got an improvement. In the document, there's suitable methods that are for sampling, where to sample and how to sample, and what are the techniques that can achieve this detection limit. The next slide just shows the rather famous table of achievable iron levels when the chemistry is optimized in the various plants. And we emphasize that this is for steady base loaded plants. For instance, if you have a feedwater system operating on AVT, achievable level of iron is less than 2 ppb. If you go to oxygenated treatment, it drops down to less than 1. In the drums, gives you the values here. In air-cooled condensers in the condensate, less than 10 ppb. But if you have a filter, we like 5 micron absolute filters, it should be able to go to 5. And so what we indicate now is that if you have higher than these values, it indicates that you have a repeat cycle chemistry situation. And you've got to be careful about adding a film forming substance, applying a film forming substance. The next slide here shows the new, just recently issued IAPS white paper. It's not quite a TGD yet because we're hoping that people will provide us with data. But this is for fast start and frequently started plants where the key indicator for iron is the decay that takes place during startup from the high shutdown level. And this is monitored by using a proxy technique such as turbidity or particle analyzers and developing this decay profile, which you see right here, and making sure that you know what is happening on the unit when you do that. That's what these vertical lines represent. So for this to be a useful technique, IAPS had to develop a template to judge if the chemistry is okay, is optimized or not. If the profile comes in the green area, that means that the chemistry is optimum, and during you've got some optimum shutdown chemistry procedures, whereas the red is the opposite, with poor operational chemistry and poor shutdown chemistries. So what I've done here is I superimpose that decay profile on here where it's in the green, indicating that this is for a well-operated unit, for operating chemistry and for shutdown chemistry. The guidance documents, the white paper gives you every indication of how you can make an improvement. But I want to emphasize here that it's not the numbers that matter, it's where this profile is. And so, for instance, with film-forming substances, you might have a profile that's up in the red to start with, and when you change to an FFS, you would hope that it would move down into the green area. But the overall emphasis is that you want to see this profile moving in this direction towards the towards the green, indicating that the chemistry is improving. So I hope you realize that this is a very powerful tool. It's one of the most exciting cycle chemistry tools that I've been involved with over the last 30 years of managing cycle chemistry. The goal is to improve the chemistry and the shutdown procedures, and you now have a tool to be able to monitor that by watching where this profile goes. I just included on the next slide a couple of examples that aren't so good, that need some improvement, and in terms of operation and in terms of shutdown. And you can see in this case the units are given here in the grey boxes. You can see in this case the profile, the decay profile is up in the red area, and it lasted for 4 or 5 hours. So this indicates that a lot of iron is going into the boiler area. In this case, not quite as high into the red, but lasting for a long period of time. So now what we're indicating is that decay profiles in the red or in the yellow indicate a repeat cycle chemistry situation, and indicates that you need to be careful about adding an FFS to make sure you know about that, or you could end up with one of those failure situations that I mentioned to you, showed you before. The third and final, as part of the Section 8 review, is to make sure you know what the internal deposits are on your evaporator surfaces. So this is an HRSG, and it's operating with optimum HRSG treatment. That means it's operating with an IAPWS cycle chemistry treatment. It's got a nice red color, which is what you want to see, and a very low level of deposits here. But the two most important things is, one, these deposits are very low, as you can see, and that there is no concentration reaction taking place at the base of this scale. You can see the deposited magnetite crystals on the surface here. There's no dark reaction products along the surface like I showed you before. Contrast that with this situation, which is an HRSG operating with a non-optimum chemistry treatment. You can see that the color of the HP evaporator is rather different than the nice red color that you want, but also you see that the deposits, the overall deposit and corrosion products are much higher, and that there is some indication of reaction products on the inside. You do not want to see those. In the former case, we would have no problem in adding a film forming substance. In this one, you need to be very careful, or else you'll end up with a situation like I've showed you. Many of you will be familiar with this, the IAPWS deposition map for HRSG HP evaporators, which we developed some time ago. This is now has been verified by over 300 units worldwide to make sure that it's providing the correct information. And so just to indicate to you again, if your deposit level, when you take the sample out, comes out in this green area, then IAPWS would suggest that it's okay to add a film forming substance. If it's in the yellow or the top of the yellow, then you need to look at those deposits to see if there's any reaction products. In other words, to see if the deposits are thick enough to allow concentration to take place. And if it's in the red area, like I showed you, particularly right at the top of the red area, IAPWS will suggest not to add a film forming substance. So these are the three tools. And again, if you have deposits in the red area, these are considered a repeat cycle chemistry situation. Don't apply a film forming substance unless you want to end up with the problems that I just showed you. So the next, just want to finish off here with a couple of research items. So as IAPWS and us individually have developed the TGDs, which were explained nicely by Wolfgang. We've also conducted many assessed plants. I've probably done over 200 plants operating with film-forming substances. We've identified from these a list of the major deficiencies and items that still need research. Unfortunately, I don't have time to go through all of these today, but I just want to mention what we consider to be the most important, and that's the effect of film-forming substances on the growth mechanisms of the oxides that grow on these surfaces in water and steam. And this is the major current deficiency. We've challenged the world 3 years ago now to come back for any of the suppliers or operators or anybody to come and provide some indication. We have yet to receive anything that's reliable. And so this is one of the major things that needs to be done. And once we have that, then we can think about, Wolfgang already mentioned, application work about changing the FFS. For example, the change from one FFS to another, not necessarily from FFP to FFA, but vice versa. And this is probably one of the major questions that I'm getting asked all the time now of how this can be done. And so these are the research items, and we have put together a draft of a ICRN. This is an IAPS certified research need. This is a document that describes what research is needed to address these film-forming substance questions. Currently, it's in review by the IAPS international members, and we hope that it'll be published in 2026, allowing operators and researchers and university research people to do the research on the right topics. And so just got a few concluding remarks for us here, in that we feel that we have a well-established and understood chemistries for more than 30 years after very large amounts of research. And that's how all of these chemistries were developed. These are the normal chemistries that everybody deals with, plus a very good, almost total understanding of the phase transition zone in the steam turbine. Whereas film-forming substances have been used in some concentration over the last 15 years without the same level of detailed basic understanding. And so no understanding of how an FFA or an FFP changes the growth of the oxide. And are there any fundamental differences between the results between an FFA and an FFP? I personally don't think so. I've done quite a few studies now. It's very difficult. Maybe the studies haven't been done in a concentrated enough way, but this is one of the things that has to be addressed. Big question is, how do we change from one film-forming substance to another? We can't do that unless we understand the answer to these questions that I've raised here about how an FFS affects the growth of the oxide. But in the interim, obviously, we've got to move ahead, as Wolfgang has indicated. We've put together a couple of little rules here. Make sure the plant chemistry is optimized before application of an FFS. And so that involves the things that I've indicated to you. A Section 8 review, monitor the iron, use the IAPS decay map, and use the IAPS internal deposit map. Second one, conduct a comprehensive review before and after an FFS application using these same tools and the Section 8 review. And use the IAPS decay map to verify improvement of iron levels. You can use this for any chemistry changes on your plant. This is a most powerful, very powerful tool. So this is where I wanted to take it today. And sorry for being a little over the hour. Just want to put this one last slide. We hope you have some questions and comments. You might have been writing some in the chat. We'll try and answer those for you now, but if not, you can feel free to contact us. Here's my work and IAPS emails, and here's Wolfgang's. So with that, I'll hand it back to Scott and David, who should have a good handle on the questions and comments for us. Thanks very much.
Thank you. Thanks, Barry. Thanks, Wolfgang. Absolutely excellent as always. Okay, guys, can you see the chat, and shall we start working through some of these questions?
Yes, I can see the chat.
So we'll start. First one that came in, a good question actually. What is the minimum period of FFP dosing before we see its effect on drum surfaces, total iron levels, in terms of when you normally start to see an improvement? He gives an example here of a plant dosed with an FFP for 6 months that saw no iron level decreases. Got any comment on that, Wolfgang? Or Barry?
Yeah, that's a very difficult question, because first depends on the plant situation, on the type of plant, on the type of FFP, and there is not a one size fits all reply. I would like to give a more general comment. If you start for the first time in a treatment with an FFS, you start with a inner surface that has no film established. There's no film established. So you have to cover first the inner surfaces of the majority of the plant until you can get significant effects. And it depends on the size of the inner surface. But with that I don't mean what is the calculated, if you take the tube diameter and the tube length, the size, but what is the real size? Because if you have iron oxide layer, it consumes a lot of the film. So I know, to give you an idea, it can take 3 months. That's normal, that you can see something really moving. You don't expect an effect that you start today and have the effect the next day. That would be probably error in detection.
I would just say it would depend also on how optimized the starting chemistry is, and there's probably a comment from IAPS that if your base chemistry isn't as optimized as possible, applying a filmer may or may not be effective in those cases. So if your base chemistry is way off the mark, that's often a problem as well. So a complex question.
We see that we don't want to spend too long on one topic, but
yeah,
we see this many times, and I see it many times with FFP and FFA, and it relates to exactly what I've said, that organizations haven't done the upfront analysis properly. Okay.
Yeah. So
I can't make it any clearer than that.
And if the plant is not operated according to the guidelines,
yes,
this is not black magic. It's not medicine for everything. Yeah.
Okay. All right. Moving on to the next one. The question here is FFAs are added in addition, for example, ammonia and ABTO. Is that correct? Is it continuous addition or only as needed? So that should be pretty easy.
Okay.
Yes. Yes.
Let me answer this. There are two options. What is IAPS preference is that you add the film additionally to the base program like ABTO, and generally it is added continuously. Keep in mind, it's a balance between the adsorbed molecule on the surface and what is in the water. So if you don't have any molecule in the water, the film is slowly degraded and removed from the surface. That's natural law. It is not spontaneously removed. There are some studies that it can take 2 weeks until it is degraded, but this is generally you have a continuous addition.
Yeah. The question is asking basically, do we add FFA by itself, or ammonia by itself, and we don't. We add the FFA as an addition to the normal
Yeah.
chemistry.
And the FFA is always in an aqueous solution, normally,
Yes.
or aqueous emulsion, because the FFS as such is a paste that you cannot reasonably handle. It's very tricky.
Yeah.
That's also maybe one comment that I should give.
Yeah, go ahead.
How do you want to address the next one, Barry? So the
Well,
question.
we don't deal with commercial products,
Yeah, and there's
but
just a question about.
we can answer it generally.
Yeah, I'll just make the comment here. There was a question asked that said a certain product doesn't thermally degrade and it doesn't affect the degas conductivity after cation exchange. The comment I'd make is conductivity after cation exchange. There are, I guess, doesn't measure everything, and you can get breakdown products that don't impact case. Doesn't mean that the product doesn't break down. It just means that it's not able to be measured by the analytical technique. So just have to be a little bit careful there. The next one, film forming aiming. So there's a question about organics here. When using film forming amines products, should we expand monitoring for organic compounds to avoid risks like first condensate corrosion? And the VGB or EN guidelines do control parameters such as feed water condensate pH or degas case need to be adjusted.
Okay, I will answer. You should. Normally, you don't need to adapt the parameters of the VGB, EN, or the TGDs from IAPS. And the film former in the majority of cases has no significant influence on pH in the dosage that we apply if it is reasonably applied. It's an amine and thus adds a little bit, tiny little bit on alkalinity, but this is normally not relevant. What is important to monitor the conductivities, also the acid conductivities. If they are in spec, then normally the risk of any corrosion is very low. So you should add to the normal monitoring the determination of the film itself, the film molecule.
Yeah, go ahead.
All right. So the next question here is probably what I think is one of the most important things out of film formers is how does the film forming substance improve steam turbine efficiency?
Okay, so we've done quite a lot of work on this, and to keep it simple, we think that the FFS in general reduce the surface tension. We've only measured the surface tension in one FFA. We haven't measured them in all the FFAs. We haven't measured them in any FFPs. And that's one of the deficiencies that we have put in the ICRN. They've got to be measured if we want to do this. Wolfgang showed you my figures from that we did with Tamara Petrova in Moscow, and that's where this was done. The work on surface tension was done at the University of Sheffield in England, but only for ODA. We'd like
I have
some
to correct
information.
you. There are data available from also from OLDA.
Is what?
There are data available from OLDA. They were
Yeah.
presented in the last conference in Prato from a
Okay.
Japanese team.
But we certainly don't have all of them measured.
That's right.
All
Go
right.
ahead.
Okay. So the next question.
I
Sorry.
can't answer that.
Yeah, there's a question just saying, what's your preferred vendors for FFA? IAPS can't answer that question. You need to do your own due diligence there. The next question was for the monitoring of the FFS, it was mentioned in field testing. However, at the start of the presentation, it was mentioned that you don't capture the product at the surface of the water, so in the field testing may not be accurate. Is there a percentage of total product that can be assumed or a correction factor that could be used?
Okay, let me answer to that. maybe there is a certain misunderstanding. Where we don't have the product on the top of the water, you have them on the surface. Yeah, and the general understanding is, and what is also something that from experience we can confirm, is that if you find a residual of the FFA in the condensate, then the film is more or less established in all the parts of the plant. What is, if you start up a treatment, it is normal that you, for a long period, that can take some 1 or 2 months, you don't find any residual in the condensate. But because you need to establish the film on the surface, so the molecule is consumed out of the water onto the surface. I hope that I made now the point clear. And so the measurement of the film in the water is correct, but you don't get what is on the surface. And that's not the intention to measure what you dose, but the intention is to have a positive residual in the water. I hope that answers the question.
Yes.
Maybe the one who has asked this can give a response.
Yeah.
Good.
Yeah, they gave you the thumbs. They gave you the thumbs up.
Good. Great. Ha. I can
So the
sleep
next
tonight well.
right, next question is a compliment to you guys, and then the question there is, will the slides be available? The whole presentation will go up on YouTube. I would suggest that just contact Barry and Wolfgang directly, and they may be able to send you a PDF of the slides. We will just post the recording of the webinar probably in a week or so once the processing is finished. The next question there, probably there's two questions here. Based on experience, what is the acceptance level of FFS application in the power generating industry? What are the main concerns? Well, I think the webinar's answered that question, but in terms of, I think the question here is what, how many, as percentage of plants who's using FFSs. I'm not sure we can answer that. You may have a good idea, Wolfgang.
Sorry, I cannot give a quantitative result on that. What I notice, it's a tendency that the power plants that are operating in heavy cycling mode, they have a tendency to have a higher acceptance for new things. Generally, the power generation market is quite conservative. It's my feeling. And if this change of operating modes, many plants gets into trouble with their water cycle chemistry, and then under these constraints, they are willing to try something additional, because there are challenges with regard to shutdown protection. If some plants are not equipped for to have an optimal shutdown protection, and if you have to be at the grid after 1 hour, you must keep everything warm. You cannot install dryers, so you must do something. Yeah, otherwise you get repeated critical situations. So that's a tendency, but it may be different from country to country. This is
Yes. But yeah, and I spent most of the presentation on what the main concerns were. I hope everybody understood that. But what is happening in the industry is that these are not generally and openly published. I only know about them because of the failure that come into my company and the metallurgical examinations that we do. We hope that presentations like this will have raised some concerns for the audience, and particularly what I find, I don't know whether Wolfgang finds the same, but I go to a lot of these plants with use FFS, and most of them have not considered to do a Section 8 review. And that's really an important aspect of the whole TGD.
yeah.
I would second those comments from Barry. We see the same things worldwide.
I showed one example where I think that at least has done a very careful baseline comparison that you sometimes also don't find. But this is a little bit crying. I think Barry made it very clear, and I think we try to make it very clear that it's the importance, and we will see what happens.
Okay. There was just a second part to this
I would
question.
like to get a comment on the nuclear plants. Nuclear plants are something very specific because then you get into the world of permission, nuclear permission. That is that's something completely different. So you need a kind of special permission to be able to add anything to the water cycle, and this makes it very difficult and not and I don't know whether there is a film forming substance that has got the general approval. Normally it's always also a case to case approval, but maybe you have other information.
There was a second part to this question about how is the FFS improving thermodynamic cycle
Yeah.
efficiency. I think the turbine's been talked about. Did you want to make a quick comment on the steam generation? Okay.
I wanted to give a comment on this slide that I showed from the paper mills. There has been studies that if you change the condensation behavior from a film condensation to a drop condensation, that you have an improved heat transport from the surface. And this is the effect of the FF. In this case, it was an FFA, I think. That after the attachment you have a more repellent surface, so that helps to get rid of the water of the heat. There are also some other stories that the heat transmission coefficient from a heated tube to the water is improved by a filmer, but this is also lacking a verification in the field. But it's very difficult to find a plant that is operating so constant that you can see the effects.
Okay. All right. Yeah. For that, the next question is, I can probably answer this one, but you can as well. Like, how do you reach a stable concentration for FFS, FFP application? Thought here that they would make the solution acidic when you transition from ammonia high pH. Probably the comment I can make is you don't change your pH, your base chemistry, and at the dose rates these products are dosed, they don't have any impact on pH generally. So if you're operating an air-cooled condenser for pH of 9.8, which is the optimum pH for those units, you wouldn't change the pH when you add an FFP or an FFS into the system.
Yeah, I fully agree. The impact of the filming molecule on the pH is under the concentrations that we use them in the water steam cycle is negligible.
Yeah. So the FFS dosing rate's always in the parts per billion as an active molecule, and ammonia is well in the parts per million.
Yeah.
The pH is controlled by your ammonia or your volatile or neutralizing amine in your feed water,
or phosphate or whatever in the drum.
Alkali in the evaporators.
Yeah, exactly.
Next one, with regards to the hydrophobicity of FFS, especially in relation of steam turbines, has there been any studies on the effects of FFS application on the last stage blade droplet erosion damage rate? That's really probably one for Barry.
Yeah.
No, it's not. It's not for me. There have been some studies to determine that there is hydrophobicity in those last stage blades, but no relation to the droplet erosion damage. That's completely different. That's mechanical droplet damage. So there hasn't been, as far as I know, hasn't been anything on that part.
Yep. All right. So next question here is about, is there publicly available information regarding the analytical methods employed by manufacturers and users for the quantitative determination of non-amine based film forming substances. So this is the dicarboxylate type products. Are you aware of any published methods for the non-amine products, Wolfgang, or is it?
No, I'm not aware.
Yeah.
Sorry.
Okay. Yep. Another good question
There
here.
we should say that there should be, though. That's one of the things that's deficient with the operation of FFP. We've raised it. I've raised it at all the meetings. We
Yes.
just had a discussion at air-cooled condenser meeting about it just in the middle of last time. But we had it the same at every FFS conference. It's, there's, as Wolfgang very nicely said at the beginning of his presentation, there's very little research done on FFP. So it's not only the instrumentation,
Yeah.
it's pretty much all the other things that we talked about.
Yeah. Some of the manufacturers have proprietary analyzers, some have in-house methods, some have in-house like little field tests. So you have to talk to the suppliers there.
Yeah.
So David, it's an hour and a half now. Is that okay? We've lost a lot of people.
Okay, up to you guys.
I'm okay.
But there's still a lot of questions.
Maybe we need to do another one. Next question. No mention of how the products
Thank you.
impact online analyzers. Do you want to make any comment on that, Wolfgang?
There are contradictory studies.
Yeah.
I personally was involved in the study of Swan that found that that there was not a significant impact on the film forming amines. I think except on the ORP that was disturbed by if I remember well. There is another news story where that sees an impact on the analyzers, which is a completely different result. In the practice, I didn't get the feedback that people were unhappy because their analyzers didn't had more maintenance work or more cleaning effects. A couple of times I had the effect that the people said, since I'm using the FFA, I don't have to clean the resins of my cationic conductivity equipment not so often anymore because the iron load is less. But this is of course not it's an indirect effect. Yeah, so I'm not exactly sure I only saw the one presentation, so I cannot comment on the differences between the methodology if there is a difference in the methodology. And it was not clear what kind of product was tested.
I'll probably make the comment from the field that part of having optimized base chemistry is also having optimized service and maintenance routines on your instruments following the OEM's recommendations. And sometimes people report issues with their analyzers where sometimes it's a failure to maintain and service and calibrate the instruments as per how they're designed to. All instruments require maintenance and servicing and generally I find that when you're dosing at optimized dose rates, there is basically no impact on the analyzers. If you are, say, not controlling your process and dosing very high rates, you may have some impact on your analytics, and you have to address that on a product by product and a case by case basis. But first and foremost, follow the instrument suppliers' recommendations and advice, and go from there. Next one here is another good question. Does the application of FFS help to stop the issue of flow accelerated corrosion? Do you want to have a comment on that, Barry, or?
I think Barry showed some impressive examples about the positive effect.
You got to remember it's single phase and two phase FAC. There's more than one.
And there is also what is also available that there are scientific studies on the effect of FFA on both one single phase and two phase FAC. And in both cases, it could be shown that there is potential improvement. Of course, there are borders. Yeah. if the conditions are too far out, nothing can help anymore.
Far too detailed to deal with here. We don't have a couple of hours, but in
Yes,
summary, what I would say, and I've done most of this work with my good friend Derek Lister, who we wrote the
yes.
paper on. So the latest paper on FAC is published. Dooley and Lister. You can get it through this system. Scott, who runs these programs, has it recorded somewhere. I don't know where it is. But basically, there's a slight disconnect between what we see in the field and what we see in the laboratory. In both the laboratory and in the field, we only think that single phase FAC can be addressed by FFS, but certainly not for two phase. We don't see consistent results for two phase FAC in the field. And I showed you that one of the best examples where you can see it is in an air-cooled condenser. In an air-cooled condenser, which is two-phase FAC, sometimes you can get it to switch off, but sometimes the same application has not done anything. There's a very it's very wide experience range there. But that's basically in summary how we look upon it.
Yeah.
All right. Okay. Next question I think is a really good one here as well. So it's about longer term preservation. Is there any guidance on the duration or durability or stability of the films? And is IAPS doing any work in this area? The IAPS ICRN covers a lot of things, but Wolfgang, you probably want to comment on if you've got
Yeah.
a properly applied system, what's the lifespan of that film under non-operating conditions?
Uh, First, we have to differentiate if we look upon standby plant filled or not filled, water filled. If the plant is, I think the more difficult case is a plant filled with water because that is, and what we see is that you get very good results uh, if you use a film former. What is important, what we normally do is that you increase the level of residual filmer in the water to significant higher levels to push the equilibrium between filmer in the water and on towards the surface. And this ensures that the film is kept instant. And if you have the usual precautions that you do during a wet standby, that you try to circulate the water from time to time, maybe once a fortnight or something like that, you can get excellent results and there's no real limitation. But if you know that you are off the road for 2 years, then normally standby under dry conditions is recommended. Yeah.
Oh,
I
go
hope
ahead.
I hope that this doesn't answer this answers the question. Okay, good. So
All right.
Oh,
Okay, so next question here is we could talk all day about this stuff, but many FFA, FFPs contain nitrogen with an unpaired set of electrons. Some of the products that Wolfgang showed in the slide are hydrocarbons with only carboxylic acid groups. Any thoughts of the potential mechanisms with these two molecules are inherently different? It's a great question.
yes, first of all, an amine has always a tendency to increase the pH. An acid has always a tendency to decrease the pH. Uh, and obviously, an acid will contribute also to the acid conductivity. That you should keep in mind. That all the carboxylic acids will lead to an increase of acid conductivity. But that's not maybe not the question. Uh, I think the principal effect is the adsorption of the surface. It has to be analyzed whether the adsorption, how stable the surface, the adsorbed surface, the absorbed layer is. Is it how fast is it reversible if you remove the additional film from the water? These are the questions that I cannot answer. Yeah, but yeah. But what I know from experience that the adsorption is faster and more fixed with an amine to a metal surface.
The exact corrosion inhibiting mechanism and mechanisms is still not very clear.
Yeah,
And that's one of the key things in the IAPS ICRN is to try to encourage researchers to clearly
yeah,
provide a clear mechanism or mechanistic kind of understanding of how these products
mm,
actually inhibit corrosion, because
mm,
we see some applications where they work remarkably well and other applications where they don't, and it's not clear necessarily what's causing the problems there. So it's a very hot topic of how these things work, and likely there's multiple mechanisms as part of that inhibiting corrosion. The next question is a very plant specific kind of request for commentary that I don't think we can really answer. There's not enough information there
mm.
for us. Are you okay to skip that one, Barry, unfortunately?
No, because it's very important because the person has missed a very important point. I tried to indicate that it's not just the coverage that matters, it's whether when the coverage at the top of the yellow includes reaction products. And they got to look at it. And so do a metallurgical examination at the same time as just measuring the standard, grams per foot squared or milligrams per centimeter squared.
Yeah. Okay. All right. The next question here is, does a scratch test on surface to see the quantity of removed deposits, I think that's a deposit weight density analysis, determine the effectiveness of FFS? FFS supplier did this and determined that there is some effect of FFP. Um,
Yeah.
you've answered those questions in here in the presentation, where you have to be measuring your total ion levels, you have to be looking at your optimized chemistry and your before and after tube analysis to see whether you've got the benefit or not.
Yeah.
Do you any other comment on that, Barry?
I don't think so. I think we've covered it.
Yeah, okay, it's good.
And for me, a
Um,
scratch test, if you cannot do it always in the same way.
yeah,
It's a matter of how strong you scratch, with what you scratch. So
yeah,
I think we generally somebody should stick with the recommendations of IAPS.
yeah. Okay. The next question here is, has there been any improvements made for field or inline verification of FFS presence in water? And I think we need to differentiate between a film forming amine,
Yeah,
where there's a number of published analytical methods, and there's also some online analyzers available from international instrumentation companies for measuring the various amines, but there is no published analytical methods for the non-amine products. And again, this is something that's been identified by IAPS as a need.
yeah.
Um, so yeah,
Okay, let's go.
probably answered that one, I think. Um, the next question here is an environmental one. How are the film formers managed at, say, waste discharge points? Because they like all the products that we use, they do have some toxicity. It's probably a comment here that they tend to degrade quite quickly once they exit the plant through the blowdown system.
Yeah.
And
First of all, we have to understand that the residual of a filmer is in a very low range. Yeah. And so, and David also mentioned that some of these molecules are readily biodegradable. So there are some tools to, for example, the ECHA risk assessment that can be used to evaluate if there is a specific risk for this specific situation. Because you have to consider that there is also a certain kind of dilution in the receiving water. So this can be managed. That are internationally acceptable tools.
Yeah.
And finally, this can be discussed also with the local water authority.
Yeah. So
And the vendor can support this process.
yeah, so you have to have a very good understanding of your water balance and your residence
Yeah.
times through your plants, and not all plants discharge direct to the environment. Some may go to sewer or may liquid discharge, and it's a plant by plant and application by
Yeah.
application.
And generally, a discharge into a sewage plant is not critical because it is absorbed, totally eliminated by the sludge.
Okay. Um, okay. So next question here. It's asking about whether film formers, if any film formers are approved by steam turbine manufacturers. They are assuming that the steam turbine OEM approval is needed for applying at a new or already operating plant. You got any comments on that, Barry or Wolfgang, in terms of do you need to get your turbine OEM approval if you're still under warranty
Okay,
to?
I am not a OEM of a turbine, so we should ask them. But I can. What is important that you stick with the steam purity specification that the OEM sets up. And if you stick to them, if you can keep them, then you are in a much better position if you violate them, especially from the point of view of warranty.
To the IAPWS steam purity document is
Yeah.
basically what we say.
Okay. So we're now into the last couple of questions, which are follow-ups. Let me just have a look at this. So
There's
the
11. There's 11.
blade droplet erosion. So they've asked a question: if you apply an FFS, smaller water droplets, does that have any, I guess, decrease, lower impact damage on the rotating blade? Barry, this is all yours, mate.
Mhm.
No, I don't have any. I don't think anything else to add. There's been no
Yeah.
work on that.
Okay.
I answered it before.
Yeah.
If this gentleman has a question, he can send me an email and I'll try and answer it for him.
Okay. So probably the next question, that's a follow-up around the length of time for storage. It's probably one for you, Wolfgang.
But
I
this
mean,
is also a very, very general question.
yeah,
Yes.
So I know a plant that had been intended to shut down for only a short period, so they did not. So they let down their plant, cool down their plant, and suddenly they were off for an unknown period. So what they did is they increased due to some circulation part-wise into the plant, they established a higher dosage of in this case it was an FFA in the water phase, and due to that they managed to get around this very difficult situation without a damage. What of course you cannot do is You cannot with this, if it is already code, you cannot establish something in the steam touched phase, like in the turbine. There you have to do something else. Or you must operate the plant for, but this normally nobody wants to do. Yeah.
I mean, this uncertainty in plant operation for cycling or flexible
Yeah.
plants, just it's a fact of life. I've lived this life in plants. You have to be on top of your chemistry all the time, and
Yeah.
you know how effective your chemistry program is part of your your routine inspections. You keep going back and saying if what we've been doing is working. Are we seeing signs of offline corrosion? In the case of dosing a filmer, is it effective for the times that we're off? And you have to provide some feedback operationally back to your market
Yeah.
people. Say, look, we can't sit for more than 6 months, and then we have to have the unit to run, or we have to go on the dry storage. And you
Yeah.
take the IAPS TGDs, you develop your own internal chemistry guidelines, you get a management approval, and you try and operate the plant to those, and constantly go back and relook at them and say, are they being effective? Are we doing
Exactly.
the right thing? Keep challenging that status quo. What other problems are we having? And go around like that.
I
Okay,
would like to have another comment. If you have a wet layup, it is important to monitor also the development of iron in the layup solution. And it's less the absolute amount, but the tendency that is important. If you get a steady increase of iron, then probably there's something wrong.
but the problem there is, say you've got a natural circulation boiler, once you're off, and you can't take a sample, right? So
Yeah,
it's very,
one
very,
death we have to die.
yeah. So, so sometimes you have to make sure that you are, as a chemistry person, you are involved in those routine statutory inspections, and you are looking for evidence that you've had high iron levels in there. You're looking for flash rust. You're looking at significant loose iron deposits in the drums or the lower headers and things like that. So there's no easy answer, right? This is the
That's
really
right.
complex, challenging end of water steam chemistry in a plant. And you know a base load unit is really easy. That comes off once a year because you can monitor everything that you need to online. When you're off, no circulation, no sampling, you can't open a window up and have a look, so it gets very challenging.
Yeah.
So that's all of our questions. Thank you for everyone that stuck that out. We've still got 60 odd people online, so it shows that the interest is there. I like to just thank Wolfgang and Barry for their excellent efforts here in putting together a world-class presentation and webinar for us. This will be published online, and look forward to our next tranche. We're trying to make these a fairly regular thing. And just as PCC chair, I'd like to make sure that everyone has an open invite to any IAPS meetings. You don't have to be a country that is a member of IAPS to attend. And you can find my contact details and Barry's contact details on the IAPS website, and reach out to us. Okay, so anything else, Wolfgang, from you?
No, I would like to thank the audience for the patience with that, exceeding a little bit our time, and all the best to you.
All right. And Barry, anything from you, mate?
No, we'll see you then. I'm going to give the next one on phase transition zone in the steam turbine, so that might be applicable to some of the questions that we got asked.
Yeah. All right. And
Right.
thanks again to Scott at Combined Cycle Journal for providing the hosting platform for this. We really appreciate your support. And and again, when in doubt with cycle chemistry, please go to the IAPS website and download the TGDs. They are all free. They are world-class documents, and most of you can find pretty much all the answers to your questions in there. And they cover almost all aspects of cycle chemistry. And there's work on the next tranche of TGDs underway at the moment. So yeah, so thanks very much.